When I started my PhD, I wanted to work on something straight out of a science fiction novel. I wanted to grow a heart in a dish. Now, while this might seem space-agey and futuristic, we actually need engineered heart cells to solve a major health problem right now. I'm sure everyone here knows somebody suffering from heart disease. Each year, nearly 1 million Americans have a heart attack. During a heart attack, up to a quarter of the heart muscle can die. And because the heart can't regenerate, those lost cells never come back. Over time, the remaining muscle can't keep up with the intense pumping demands of the heart and fails, leading to the disease we see. Our hope is that by growing heart cells in the lab, we can provide patients with regenerative therapies that help them truly recover from heart attacks. Now, we've already made tremendous progress on this front. Over the past decade, researchers have developed methods to turn renewable stem cells into cardiac cells in a dish. Now, these cells are really extraordinary. You can actually see them beating under the microscope. So it seems like we're already pretty close to our sci-fi fantasy, right? Unfortunately, these engineered cardiac tissues look more like baby heart cells rather than adult heart cells. They don't quite pump hard enough to be useful for patients. We need these immature cells to grow up somehow. Researchers have already tried a number of methods to mature these cells, such as stretching them or shocking them, but so far we still seem stuck with baby heart cells. My PhD thesis aimed to tackle this problem from a different angle. If we want our engineered heart cells to grow up, we should figure out how Mother Nature does it in the first place. Thus, I tried to understand how heart cells mature inside of us when we're growing. I found that there are 9 transcription factors. You can think of these as molecular switches that need to be turned on for the heart to mature. In engineered cells in a dish, however, these switches remain off and the cells never grow up. I also found that previously tried approaches, like electrical or mechanical stimulation, could turn on 1 or 2 of the switches, but never all of them. We're currently using CRISPR-based genetic approaches to turn on these transcription factor switches in the lab so that we can grow the mature heart muscle our patients urgently need. I hope that my PhD thesis can help us take one step closer from turning that heart in a dish science fiction story to a clinical reality. Thank you.